Hello friends, today we'll be discussing about codes and K-maps in basic electronics. I'll be explaining about binary codes, weight, non-weight codes, gray code, and error detection and error correction codes. After that, we'll be discussing about K-maps. Okay, now starting with codes. We all know that in computer we don't speak to them in normal language. We use something called binary code, and binary code is nothing but the data is in the form of ones and zeros. Now there are two types of binary codes primarily, and one of them and they are weight binary codes and non-weight binary codes. Okay, now I'll take an example and explain, because in that way it is easier to explain. Let us say we have a 4-bit code, and let us say this is weight code. Now I'll be explaining about 8421 weight binary BCD code. This is a weight binary code. So indirectly, weight code means every digit of these 4 bits have some weight to them. For example, the weight of this first unit digit is 1, and tens is 2, hundreds is 4, and thousands is 8. Okay, now let us say we have a code 0 0 1 1. Okay, now for the decimal form of this 8421 BCD code, you have to multiply the numbers with the specific weights. That is, so the decimal form of this will be 0 into 8 plus 0 into 4 plus 1 into 2 plus 1 into 1. That is nothing but 2 plus 1, which is 3. This is decimal form of 80011 BCD code. Now we might get confused here. Binary code and BCD code are not same. In BCD code, you can represent numbers only from 1 to 9. We cannot represent codes after 9, that is for double digit numbers. So as we know, the binary code of 9 is nothing but 1001, and the same, and BCD code of 9 is also 1001. But for double digits, let us say example 10, the binary code is 1011, 1010, not 1011. So that is 8 plus 2. But for BCD code, 10 is not represented as 1010. In for BCD code, for all the double digits in BCD code, we represent them digit by digit. We write 1 separately and 0 separately. That is, for 1 it is 0001, and for 0 it is 0000. So 10 is represented as 00010000 in 8421 BCD. This is nothing but 10. But primarily we will not be using double digits anywhere in our calculations, and we'll be discussing about don't care terms later, where this plays a major role. Okay, this is weight BCD code, and there are also other weight BCD codes such as 7421 and 4221, where again the unit's position takes 1, and the tens position takes 2, and hundredth position takes 4, and thousandths position takes 7. This is 7421 BCD code, and if it is again 0011, for the same example, let us say we should multiply them with 7 instead of 8. So indirectly 7421 means the weight of the digits are 74211. That is, again it is 3 because I have not multiplied anything here. And same follows with 4221. I will not be explaining it because again the weight of units is 1, tens is 2, hundreds is 2, hundreds is also 2, and thousands is 4. Okay. Now moving on to non-weight codes. Okay. Now moving on to non-weighted codes. Here we have excess code, XS3, XS3 code. Okay. Now non-weighted, as the name specifies, the positions of the bit does not carry any weight. This can also be written as XS3, and as the name states, there is no weight. So how is it obtained? For XS3 code, all the codes in XS3 are obtained by adding 0, 0, 1, 1 in binary to BCD code. For example, BCD code of 9 is 1011. See, 1001. Sorry. And to get XS3 code of 9, we should simply add 3 to it, 0011 in binary form, which gives us, if we do that math, so 1 plus 1 is 1, carry 1 and sum is 0, and again 1 plus 1, sum is 0 and carry 1, 1 plus 0 plus 0 which is 1, and 1 plus 0 plus 0 which is 1. See, so now 1, 1, 0, 0 is the XS3 code of 9. Okay, now as you can see on the screen, 0 is represented as 0, 0, 1, 1. 9 is represented as 1, 1, 0, 0. The speciality of XS3 code is it is a self-complementing code. Self-complementing code in the sense the 9's complement. For the 9's complement is the sum of two numbers should be 9. So the 9's complement of 0 is 9. 9's complement of 1 is 8. 9's complement of 2 is 7, that way. So as we can see from the screen, the 9's complement of 0 is 9, and the code of 0 is 0011, and code of 9 is 1100. We can simply obtain 9 by reversing the digits, replacing zeros with ones and ones with zeros. Same applies for 1 and 8, 2 and 7. As we can see, 1 is 0100, but 8 is 1011, which is nothing but replacing all ones with zeros and all zeros with ones. So we can say that XS3 code is a self-complementing code, where you can just obtain the 9's complement by swapping the digits, swapping zeros with ones and ones with zeros. Okay, now we'll be discussing about the next code, that is a gray code. In the gray code, it is not a decimal code, it is not an arithmetic code. The only speciality about gray code is the code of each digit, let us say code of 0 and 1 and 1 and 2, they differ by only 1 bit. So in gray code, the code of 0 is 0000, but the code of 1, okay, let me keep it. But code of 1 is 0001. There is only 1 bit difference. And code for 2 is 0011. Again, there is only 1 bit difference. Just like code for 3 also, let us say for example 0010, there is only 1 bit difference. Like this, all the codes of the numbers, especially the codes of the numbers after them, like 5 to 6, 6 to 7, they differ only by 1 bit. Let us take 5 to 6. 5 is represented as 0111. This is not a binary code, and this positions does not carry any weight. So the code for 6 will be 0101. It differs only by 1 bit. And for 7 it is 0100. Again, it differs only by 1 bit. Like that. This is gray code. Parity codes or error detection codes. First of all, let me say one thing. So all the electronics, all the wireless signals are transmitted through a very noisy signal. Let us say all the electronic devices such as Bluetooth or Wi-Fi works in a single frequency, that is 2.4 gigahertz frequency, and all of them have to work in this. So there's a lot of noise, and there's a very high chance that signal can be distorted. That is, let us say 4-bit code. If the transmitter sends 1111 as code, there is a high chance that there might be some error such as 1011 or 1000, something like that. There can be errors. So to avoid all these errors, we bring in parity codes. Sorry, not to avoid, parity codes or error detection codes can only detect if there is any error but cannot correct them. We will be discussing about correction after this. Okay, now parity codes. There are two types of parity, odd parity and even parity. Odd parity of 0 and odd parity of 1, even parity of 0 and even parity of 1. Let us say there is a code of 4 bits. So at the end we add a extra bit called parity bit, which tells if the code is correct or not, if the code from the transmitter is received properly or not. Okay, now let us say there is a code 1000. Now if we say this is odd parity of 0, as we can see there are 3 zeros in the data code. This is a parity code and this is parity bit and these are data bits. As we can see there are 3 zeros in the data bits. So if we say that the code is verified using odd parity of zeros, this should be replaced by 1. This is because we already have 3 zeros. So 3 is an odd number. So when transmitter receives this signal, it understands that there are 3 zeros and it is odd parity of 0, and we have replaced the entire code with 1. So there are 3 zeros and therefore the code is correct. But let us say while transmitting this code has been changed to 10011. Let us say this bit is swapped, and when the transmitter receives it, it knows that according to the rules there should be actually odd number of zeros, but there are even. So it rejects this code because it detects the error. If it is even parity, let us say it is even parity of zeros. Now as we can see there are odd number of zeros. We can simply keep a 0 here to make all the zeros on all the number of zeros even. So when the transmitter receives something like this, it knows it is wrong because there are odd number of zeros. Same follows with 1. Let us take a different code, 1011, and this is the parity bit. So if it is odd parity of 1, we can see there are 3 ones. So it is already odd number. We simply keep the parity bit as 0, and there are odd number of ones. So if something changes like this, it knows that it is wrong. Moving on to even parity of 1, again taking the same code, as we have a odd number of ones here, we add one more 1. That's it. Now this says that this is even parity of ones. When the transmitter checks for even number of ones, and if something is changed, let's say the parity bit in itself is changed, it flags it as an error. But now let us take a different scenario. In any of these cases, let's take the last case where it is even parity of ones. Let us say instead of this, there are 2 bits that are flipped. So now we can see there are 2 ones. It is nothing but even number of ones. Transmitter will simply not detect this error because there are two errors, which will again lead to even number of ones. So transmitter will simply not recognize this. This is the limitation of parity code. It can simply detect, and it can also fail sometimes. So for that, error correction codes have been introduced. Okay, now error correction codes are nothing but Hamming codes. These are also error correction code. This cannot just detect but can also correct the code. Okay, we will be discussing about 7-bit Hamming code. And in this 7 bits, The 4 bits are data bits and 3 bits are appended inside this 7-bit code, which are nothing but parity bits. These bits decide if the code is correct or not. Okay, now let us discuss about Hamming codes or error correction codes. Before I can say anything about this, first I would like to speak about Hamming distance or D minimum. This is the difference in this. I'll take an example and explain it. So let us say a circuit accepts two valid codes. Let us say they are 0, 0, 0 and 1, 1, 1. As we can see, all the 3 bits have been changed. So minimum distance of this is 3. That means the minimum number of bits that have been changed for one valid code and the next valid code that a circuit accepts is called minimum Hamming distance. And the valid codes that the circuit accepts, in this case 0, 0, 0 and 1, 1, 1, are called valid code words of the circuit. Now let us say a transmitter has transmitted signal 0, 0, 0 and receiver has received signal 0, 0, 1. Now the receiver will compare it with the two of the valid codes for circuit 0, 0, 0 and 1, 1, 1. Now as we can see, between 0, 0, 0, 0, 0, 1 and 1, 1, 1 there are 2 bits that have changed. But for 0, 0, 1 and 0, 0, 0 there is only 1 bit that has changed. So the circuit will assume that there is like a high chance of only 1 bit has changed and it will take 0, 0, 0 as the correct code. Yes, and the code has been corrected and that is what we are actually trying to send. Let us say the minimum distance is only 2 and there are minimum distance is 2 and there are, let us say, two valid code words. Now we send the signal 0, 0, but let us say due to noise and disturbance the receiver receives it as 0, 1. Now if it compares it with the valid code words, there is exactly one difference between the first and second. So it doesn't know which is correct. That's why the minimum Hamming distance is 3. Okay, now I'll be explaining about how Hamming codes actually work and how it is able to correct its code. Before that, we will be discussing about 7-bit Hamming code. In this 7-bit Hamming code, 1, 2 and 4 bits are parity bits, 3, 5, 6, 7 are data bits. So let us write them like this: 1, 2, D3, D4, D5, D6, D7. 1, 2 and 4 are parity bits, whereas 3, 5, 6, 7 are data bits. Okay. Now I'll be explaining how it checks parity, how it confirms there is no error, and how it is transferred using an example. Okay, now let us say we need to transfer a code 1, 1, 0, 1. So data bits D3 will be 1, D4 will be 1, sorry, D5 will be 1, and this will be D6, this will be D7. Okay. Now the parity bit P1 checks the positions 1, 3, 7 and 5. Parity bit P2 checks the position 2, 3, 6 and 7. Parity bit okay, not P3, P4 checks the positions 4, 5, 6 and 7. From here we can see for checking parity bit P1, so first bit, that is P1 itself, and third bit, that is 1, 7th bit, that is also 1, and 5th bit, that is 1. Okay, now here the parity bit here always follows even of 1. So it always tries to even out the number of ones present. So if we check to even out this number of ones here, P1 should be 1. So P1 is 1. Next, P2. Parity bit 2 checks positions 2, and 3 that is 1 and 6 that is 0 and 7 that is 1. So to make here it is as it is even parities of 1, P2 can be 0 because there are already two ones. So P2 is 0. Next P3. P3 checks P4. P4 checks fourth parity. P4 is the fourth parity bit and it checks fourth position, fifth position which is 1, sixth position which is 0, seventh position which is again 1. So from here if you see again P4 there are two ones already present, P4 also will be 0. So the entire data code will be 1 0 1 0 1 0 1. Okay. Now let us say this code is transmitted and let us say there is some error. Let us say this bit has changed. 1 0 1 0 1 1 1. Now again at the receiver it again checks. Let us say it checks from C1 which checks the positions 1 3 5 7. Okay. Now if you see one position is 1, third position is 1, fifth position is 1, seventh position is 1. So all of them are 4 ones. So it is even. So because it is correct, C1 is assigned a value 0. Whenever the check passes, it is assigned a value 0. So next C2. C2 checks second position which is 0, third position which is 1, sixth position which is 0. Sixth position is 1. Sixth position which is 1 and seventh position is also 1. Here this is odd number of ones. So the check fails. C2, the check fails. So it will be assigned value 1. Next C3. C3 checks 4, 5, 6, 7 positions. So fourth position is 0, fifth position is 1, sixth position is 1, seventh position is 1. Again, the C3 also fails because there are 3 ones. Okay. Now the data bit C3, C2, C1 which is 1, 1, 0 is called a syndrome bit. Now if we see this as a binary code, this is 2 power 0, the weight of this position is 2 power 0, this is 2 power 1 and this is 2 power 2. If we add it, that is 4 plus 2 plus 0 which is 6. It exactly tells us the position of the bit which has an error. As you can see 1, 2, 3, 4, 5, 6. Sixth position has an error. This syndrome bit tells us that error is in sixth position. So the receiver simply flips this bit and takes the correct code. This way 7-bit Hamming code is used for identification and correction of the code. Okay, now we will be discussing about Minterm, Maxterm and canonical forms. Okay, now there are two types of Boolean expressions, sum of products and products of sums. So let me start with sum of products. As the name states, the Boolean expression is comprised of sum of many products of many variables, that is or form of many ANDs. For the entire explanation, I will be taking 3 variables, let us say A, B and C. Okay. Now, let us take an example of some random Boolean expression. Let us say AB plus B bar dot C plus A, B, C bar. Okay. Now, as we can see here, A, B does not contain C, neither not in normal form or in complemented form. B bar dot C, here it is the same. It does not contain A, not in normal form, not in complementary form also. But this specific term contains all the three variables of the function a, b and c. Does not matter if it is normal form or complementary form, but it contains all the three terms. So this specific term is called minterm. A minterm is one term of the entire Boolean expression which contains all the three variables in any form of the variables, it is complementary form or normal form. Okay. Now, if all the terms of the Boolean expression contains all the variables, that means if every term of the Boolean expression is a minterm, then that is called canonical form of SOP, canonical form of sum of products. So now to convert this into canonical form of products, will be using a property. We all know if x is a variable and if we add it with x bar, it is 1. So we can write this as a dot b dot 1 plus b bar dot c dot 1 plus a b c bar. We can replace this ones with whatever the variable is missing. So here we have c missing. So replace it with that. C plus c bar, b bar dot c dot a plus a bar, a b c bar. Now we'll use distributive property a dot b dot c plus a dot b dot c bar plus b bar dot c dot a plus a bar b bar c plus a b c bar. Now if there are any repeating terms, just eliminate them. As we can see here, a b c bar, a b c bar, it is repeating. We can just merge them. So the final Boolean expression will be a b c plus a dot b dot c bar plus a bar dot b bar dot c plus a dot c dot b bar. This is canonical form. Canonical form of sum of products, because this contains all, this has all the terms of this Boolean expression are minterms. Okay, just like that. Now we'll go for product of sums. Again, just like the name states, this is all the terms of this Boolean expression are, this Boolean expression is of is a product, but the terms are some terms. It is something like this: a dot b bar, a plus b bar dot c plus a dot a plus b bar plus c, let us say. As you can see here, this contains all the three variables of the function of product of sums of the Boolean expression. So this is called a Maxterm instead of a Minterm. So now we'll use a different property here. 0 can also be written as x dot x bar. If we do AND for a variable and its complement, we end up with 0, and we can simply keep a plus 0 there. So a plus b bar plus, as this can be written as a plus b bar plus 0. Now we'll replace this 0 with missing variable, that is c dot c bar. A plus c bar plus b dot b bar. A plus b bar plus c. Now again we use a reverse distributive property here to expand these both terms. The reverse distributive property goes something like this. Just a second. If there is a plus b dot c, it can be written as a plus b dot a plus c. But instead of a here, we have a plus b plus something else. So this can be written as a plus b bar plus c dot a plus b bar plus c bar. A plus c bar plus b dot a plus c bar plus b bar dot a plus b bar plus c. That's it. So I don't think there are any missing terms. No, I was mistaken. There is indeed a repeating term. So as we know, a dot a is nothing but a. So just replace it with A dot A. Okay, we have one more term as well. So that will be A plus B bar plus C dot A plus C bar B bar plus C bar dot A plus C bar plus B. Okay, this ends the explanation of minterm, maxterm, canonical form of sum of products, and canonical form of product of sums. Next, we'll be discussing about K-maps.